This video will be an introduction on the regular grammar. So, you should be reasonably familiar with languages and know that there's a special set of them called the regular languages. You should understand finite state machines reasonably well. You should definitely understand regular expressions, and particularly you should understand what tuples are, because we're going to use them to formally define the regular grammars in the same way that we did for finite state machines and the same way that we will for most of the things that we define in this course. So, on the left here we have a simple regular expression that from your last video you should understand means the language made up of strings that contain 0 or more A's because of this clean star, followed by 1 B and 1 C. So that could include the string BC. It could also include the string with 10 million A's followed by BC. On the right hand side here we have the regular grammar, or a regular grammar, for the same language, and by the end of this video you should have a rough idea what's going on here. So, formally a regular grammar is a 4-tuple consisting of the elements V, sigma, R and S. I'm going to define them out of order. It'll make a little bit more sense first. So the second element, sigma, is exactly the same sort of input alphabet as we have with a finite state machine. So if our language is a language like we described before that could consist of A, B's and C's, then sigma will look like this. Nothing particularly new. R, the third element here, is a set of rules that we use to build up the strings in the language from a starting symbol. I'll describe these in more detail later. V is an alphabet a little bit like sigma, except it consists of symbols which are not allowed to appear in the input string. So before we had sigma was the set A, B, C. In this case, V is not allowed to contain any of those symbols, and V is used within the rules here to help us build up the strings from a starting symbol in V. And that starting symbol is the final element of the regular grammar. So it is an element of V that we start every derivation of a string from. So every time we're trying to build up a new string from the language, we start with whatever this symbol is. Now often in our grammars we will actually use a big capital S, but it could be any symbol within our non-terminal alphabet. So to sum up, we first have our non-terminal alphabet V, our terminal alphabet or input alphabet sigma, our set of rules, which is actually the most important part of the grammar, and a start non-terminal, which is one of the symbols from the non-terminal alphabet, kind of like the start state in a finite state machine. Now technically the alphabets V and sigma can contain any symbols in them as long as there's no common symbols between the two. But when we're doing little exercises where we're working with strings that we commonly use lowercase letters for in sigma, we typically reserve uppercase letters unless we need them for elements of V just to make it stand out in our rule sets. So that's what I'll be using in the next slide. So the only really new thing with a regular grammar is the rule system R. It's a simple rewrite system. And by that I mean we have rules that look like this, where we have something on the left hand side which we can replace with whatever's on the right hand side. For a regular grammar, on the left hand side we're allowed to have one non-terminal, and on the right hand side we're allowed to have one of two things. We can either have a single terminal, or we can have a single terminal followed by a single non-terminal. So if our sigma, our input alphabet, consisted of A's and B's, and our non-terminal alphabet consisted of capital A's and capital B's, then the following rules would be acceptable. Big A goes to little a, big A goes to little b, capital A, but the following rules would be obvious obviously not be allowed. So little a goes to anything, any number of multiple symbols on the left-hand side, goes to something, or rules where we have something other than a single terminal, or a single terminal followed by a single non-terminal on the right-hand side. So rules with say AAA, even AA, or just a single non-terminal would not be allowed. The way in which we produce symbols from the language is we start with our single non-terminal. So in this case, if our single non-terminal was perhaps A, then we take that and we continue replacing it with a rule that matches it. So if we had the following two rules and say another rule that doesn't match it, we could use any one of these two rules, but we would not be able to use this rule to replace. So for instance, we could use the second rule and replace that with AB. We continue doing this, choosing one of the non-terminals arbitrarily and replacing it with a matching rule from R, until what we have left is just a string consisting of terminals. And at this point, because of the rules that we've decided for in our rule system, because they are not allowed to take anything on the left-hand side that is not a non-terminal, we halt, and that is one of the that resulting string of terminals is one of the strings in the language. So in this case, we would now, considering the only non-terminal we have left in the string is capital B, be able to replace it and spit out the string AB. So just a quick example using this following grammar here. So this grammar consists of non-terminals that are a capital S and a capital X, terminals that include A, B and C, so all of our strings have to be made up of A's, B's and C's in the language, and this rule set here, which consists of 3 rules. Now note that if we have a rule set where we have a non-terminal in V that doesn't have a matching rule that is on the left-hand side of it, it doesn't make much sense because we can never expand that non-terminal. But that aside, our start symbol, our start non-terminal, is S, so we start the string off with an S. We can then use one of these 2 rules here to replace it, and so I'm going to choose the first one. So I'm going to replace that with A and then another S. Then I'm going to arbitrarily pick the second rule, and we can pick any rule that we want, and I'm going to replace the S with B capital X. So you can see how we gradually build up strings. Then, the only rule that I'm allowed to use now is this final rule here, which turns the capital X into a C. So I replace that. And now my string consists only of terminal characters, and I can halt and return the string ABC. So ABC is one of the strings in the language described by this regular grammar. So, I told you by the end of this video you would have a rough understanding of this particular grammar here, and that is the one that we just covered in the previous example. So I don't expect you to be completely fluent, but you should understand have a rough understanding of this grammar here on the right hand side, which you will learn later, you will learn how to decide later, actually represents the exact same language as this regular expression here, and the exact same language as a number of finite state machines which you'll be able to build from either this regular expression or this grammar. So, by now, you should be familiar with what a regular grammar is, in particular its formal definition as a 4-tuple, and you should understand the basics of how the rules operate as a rewrite system, but you'll go over this in more detail in lectures.